I'm Bill Grob, Director of the National Center for Supercomputing Applications at the University of Illinois and Vice Chair of SC20 Invited Talks. Welcome to the SC20 Invited Talk session on quantum futures. The overarching theme of SC20 is more than HPC. Complementing this theme, the Invited Talks collectively focus on applications and technologies impacting all areas of science, engineering, medicine, and society. The distinguished speakers in this session will provide insight into the fascinating world of quantum computing technologies and on how it is rapidly evolving with the potential to shape the future of computing. Göran Wendin is a professor at the Department of Microtechnology and Nanoscience at Chalmers University of Technology in Gothenburg, Sweden. Over the years, his research has involved dynamics of many electron systems, atom-laser interaction, electron transport in nanostructures, Andreev levels in Josephson junctions, and more recently, quantum computing with superconducting circuits. Since 2000, he has coordinated 5 major EU projects on quantum computing with superconducting devices. He is currently a work package leader in the Open SuperQ project in the Qt flagship, and a PI in the Swedish WACQT project, both with the mission to build a European superconducting quantum computer.
My name is Göran Wendin, and I'm from Chalmers University of Technology, Quantum Technology Group in Gothenburg, Sweden. I'm going to talk to you about quantum futures, quantum computing in the NISQ era. The present reality is that real-world applications can already be executed on quantum hardware processors with effectively 10 to 15 qubits. Important current use cases are optimization and quantum chemistry. However, quantum processors are noisy intermediate scale quantum devices. The term NISQ was invented by John Preskill at Caltech a few years ago. So with these noisy intermediate scale devices, coherence times are limited and gate fidelities are limited. So the depth of quantum circuits and the length of computations are necessarily severely limited. The quantum volume was introduced by IBM a few years ago and is an effective measure that integrates the effects of number of qubits, connectivity, coherence times, and gate fidelities. And the quantum volume indicates the number of entangling gates that can be performed within the coherence times. It sets limits on the length of and complexity of quantum circuits, and it provides a fair measure for comparing the performance of different types of qubits and platforms. So in an ideal fully connected quantum computer, the quantum volume is 2 to the n. So if n is 6, the quantum volume is 64. The current state of the art is actually quantum volume equals 64. It's achieved by Honeywell with a 6-qubit ion trap, which is fully connected. That means all qubits communicate with each other without swapping. And IBM on a 28-qubit processor of superconducting transmons, which was sparsely connected and noisy and therefore far from ideal. Regarding architectures, superconducting transmon network, you see there in the middle up top picture, that's a transmon network there. The picture then to the right shows an ion trap where a string of ions are vibrating and then coupled together by their effective ion vibration bus. The neutral atom architectures involve optical traps, interference patterns by interfering lasers, and they are filled with Rydberg atoms. And the semiconductor devices are made out of spin qubits. They use spin qubits, and they are formed by quantum dots or implanted impurities. So here is where I am at home. This is our lab, and this is Wallenberg Center for Quantum Technologies, which is a 12-year project with a mission to build a quantum processor with 100 to 200 superconducting transmons. Of course, compared with the big industries, this is a very modest project, but the goal is really to produce high quality. That's very, very important. So why do we need quantum computers? Because we desperately need exponential speed up to be able to solve approximately NP-hard problems with finite resources in terms of time and memory. The original killer application, as many of you know, is Shor's algorithm for factorization from 1995. Today, however, the typical killer applications are what we call use cases: quantum chemistry, designing enzymes and catalyzers; materials science, describing strong electron correlations; and optimization, logistics, scheduling, travel and salesman type of problems. So there is no lack of algorithm and applications. What is lacking is large-scale, high-fidelity quantum hardware. Quantum computers offer, in principle, exponential speed up for certain classes of hard problems. So the time to solution for a classical computer grows exponentially, while the time to solution for a quantum computer grows rather polynomially. So so as long as the problem size is not very large, there can be no quantum advantage for a quantum computer. So the problems will probably need a few hundred qubits in order for a quantum computer to get an advantage. The QC relevant, the quantum computing relevant complexity classes are P, BQP, and QMA. And the P class is where high performance computers are efficient. This is polynomial time. And BQP is the bounded quantum polynomial, is where it's hard for classical computers, but it's easier for quantum computers. It's efficient there, and it give quantum advantage. And then in the end, also QMA, quantum Merlin-Arthur, it's hard for quantum computers, so it's hard for any system we can imagine. So here's the big picture, and you see there P, BQP, and QMA. And on the border between BQP and QMA, you have this interesting region that is hard for ordinary quantum computer. There you find really what we want to do: materials chemistry, material science, and quantum chemistry. And so it's clear that that is living in a very difficult region, and we can basically even only look for approximate solutions, even with a quantum computer. So quantum computing is all about quantum physics, right? So one way to look upon quantum computing is that it solves problems by generating and interpreting dynamics of quantum wave patterns in registers of quantum bits. So the Schrödinger equation, as you see there, provides a wave function picture, and it provides an analog side of quantum computing in terms of wave function and interference patterns. So the left picture you see there is, as you can see, of course, water on the surface, but the pattern there, which could be rain or could be throwing stones in the water, there the pattern actually computes, if you like, the perturbations caused by throwing stones into the water. So the stones then are sort of the gate operations, and the pattern is the solution. And there on the right you see the digital side, where we rather say the Heisenberg picture and linear algebra superposition entanglement. So there the wave function is now a state function and a superposition of all configurations that the register can have. So each of those configurations you see there, 000, it says, or 0001, represent configurations that a classical computer can only have instantaneously. You cannot superpose them in a classical system, but in a quantum system you can do it. And if the coefficients there are such that the result is not factorizable, it means it's entangled. And then is really where you have the quantum effect. I mean, the power of the quantum computer. So in the picture to the right, and the top picture there with the red and blue patterns, there you see a stadium of iron atoms put down by a scanning tunneling microscope, and the red area is electron gas from a copper surface. So the iron atoms work as gates, inducing this pattern in the electron gas, which is then the solution. And in principle, you can imagine moving around the atoms and creating patterns as a response to gates, if you like, operating gates. And then the interference pattern would be the solution. So now, if a little girl wants to do a quantum computation, she will call up a classical front end and introduce a problem. And if it's a quantum problem, the classical machine will consult its accelerating part, which will do a computation in memory. Here you see a little details of that. The quantum computing involves the state of a single multi-qubit memory register. So it's computing in memory. So on the left, these states there, you see 0, 0, 0, 0 down to 1, 1, 1, 1. That is then a superposition with equal coefficients, you see. So if you see what that is, it's what you see just below. It's a product of 0 plus 1. Each qubit is entangled, is superposed, 0 plus 1, but it's a product of such. So it means that you sort of have tilted the spins of the qubits down to the equator, but they are still not entangled. So this is a very common starting point for a quantum computation, because from then on, you can control CNOT gates, control NOT gates, using those kind of superpositions. And then you use this time evolution operator, UTT0 up there, to evolve the state to a new state. And there you then end up with a time-dependent state with time-dependent coefficients. And that is then a superposition again of 2 to the n states, but now it's entangled. In generally, it's entangled, so it's not factorizable. And a state that is not factorizable like that is quantum. So it involves quantum correlations and quantumness, and that is the difference to a classical computer, which only can produce product states. So in order to do all of these things, you need a complete stack. And that exists already in many services already existing by Google, IBM, Amazon, Alibaba, etc. So it contains high-level languages that already very functional, and then they driving a lot of software all the way down to the hardware at the end, where typically the software is driving microwave sources, for instance, to flip qubits. So here you see just two examples of superconducting quantum processes. So the performing art is actually, as far as I'm concerned right now, the 53 qubit Sycamore chip of Google, and the IBM 65 qubit chip Hummingbird of IBM. If you want to understand how a superconducting transmon qubit works, it's actually very easy, because up to the left there you see an LC circuit, and that's just an harmonic oscillator, right? And you see there then the sort of the potential and the energy levels in that potential, and they are equally spaced. You see n plus 1/2 times h omega. And you can make superpositions of that, like A0 plus B1 plus C2, etc. Right? You can build up superposition states. But then going to a superconducting qubit transmons, one complements that inductance with a Josephson junction, which means that you then have a nonlinear inductance. So that means that the harmonic potential of the LC circuit is now becoming nonlinear, and you have an anharmonic oscillator where the distance between levels is no longer equal. That means that you can actually address each transition, each distance between levels there individually, and they can form qubits. And that is, as you see, then defines the qubit of the transmon. So here you see some examples of circuits, single qubit. Up left top corner, you see a transmon qubit connected to an LC oscillator capacitively, and below you see how that is done by a coaxial waveguide. And the bottom picture there extrapolates to few coming experiments, existing experiments, but coming devices maybe where you can actually couple to optical fibers. This is what is needed in future. And then top right, you see two qubits, transform qubits, through various types of fixed or tunable couplings. And tunable couplings are essential now for actually building large systems for flexibility. And some of this you see in real applications below in this picture by the ETH Zurich group of Andreas Wallraff. And this is part of the Open SuperQ flagship project. And there they actually do some very advanced experiments for repeated quantum error detection in a surface code, which is sort of laying the foundations for future work. So what about computing then? Because the limited coherence time makes it necessary to limit the number of quantum gate operations. So what can we do? Well, we have to chop up the computation in not too long pieces, where with operations that can be done within the coherence time. So, and that means we go for hybrid systems and quantum variational methods. So that means, for instance, Rayleigh-Ritz variational principle, and you try to minimize the expectation value of a cost function. And for that, you need a trial function. Schemes using this kind of approaches is the quantum approximate optimization algorithm, QAOA, or the quantum variational eigensolver, VQE. Okay, so here you then, in the middle of the slide, you see a quantum register, and it's first reset to 0, 5 qubits, and then a number of gates are applied to form a superposition state. You see that in the middle with 5 qubits, with coefficient A1, 2, 3, 4, 5. And that state, in order to compute with that, you are actually, in order to use it for optimization, you have to actually measure and read out a snapshot of the state function. You cannot read out the superposition. So quantum physics collapses the state when you measure it. You get one of the possibilities. So you have to do quantum state tomography and actually get a distribution of states, which you then will use for evaluating the cost function, which you then use to minimize the energy, and then you update the parameters, and then you run around until you have some sort of convergence on the energy or the cost function. And you see down there, well, the Hamiltonian is scrambled, but you can probably understand that the first part is the Ising piece with 1 and 2 Pauli operators, while the right part involves 3 Pauli operators, and this is just the beginning of a long series which describes electron correlation when you do fermionic problems. My own interest in this is partly to do prebiotic molecules, to compute. It's for benchmarking, actually, quantum chemistry packages, but it's also a very interesting topic in itself, because life requires molecules that combine flexibility and organized metastable structures needed for function, adaptation, and evolution. And essential there is hydrogen bonding which keeps, for instance, DNA rungs together, but also is part of very important chemical reactions, like keeping this polyimine to the picture to the right there. Polyimine is sort of a potential starting point or a useful substrate for doing prebiotic chemistry. For instance, the atmosphere on Titan, which I think is Saturn's moon, contains hydrogen cyanide, and it's possible that some prebiotic processes go on in that atmosphere. So, application to prebiotic molecules. This is for benchmarking actually Qiskit through the variational quantum eigensolver. So we use both the minimal and more advanced orbital basis. The starting point is Hartree-Fock, and the variational trial function UCCSD excites configurations out of Hartree-Fock using single and double excitations, creating then excited configurations. And we need a fermion to qubit transformation. I mentioned before Jordan Wigner, but here is one is called parity. It's developed by IBM, or actually it was developed by Sergey by IBM, I think. Optimizer is SC20, sequential least squares quadratic programming. In this application to prebiotic molecules, you see there to the left a number of molecules that are of interest, including hydrogen bonding and water change. You see that chemical picture there, showing how hydrogen is keeping water molecules together and creating this interesting structure that water has. And moreover, down there you see number of qubits increasing up to rather impressive numbers, right, near 100. And we have discussed this in this paper that you see on this slide. So I'm now showing you two examples. For the NCCN, we used a minimal basis set far from chemical accuracy and used the VQE, and the STO6G, there's a minimal basis. And actually, look to the right, I was using an iMac i9, 8 cores with 128 gigabyte RAM, so it's a pretty good machine. It's not a supercomputer, of course. Although actually each processor there, I mean, is as good as what you have on the supercomputers. It's just that the supercomputers have a lot more of it. So anyway, here it turns out that with this 29 qubit system, you need almost 3,000 variational parameters and 500,000 gates. Circuit depth is 500,000, and the one single energy evaluation of one value for a variational parameter is 5.5 days. Now you have to multiply that then by 2,815 to get one single energy iteration that can then go into the optimizer, and that takes about 10 iterations to get a solution typically, and that's 424 years. So Summit would need 6 days for that. A quantum computer, let's say a rough estimate with 50 nanoseconds per 2-qubit gate time, you would end up around 10 minutes for 20 milliseconds for each quantum run. But then together with everything, classically, you would end up around 10 minutes. And that's really minimum. Now go to the more advanced example. Actually, the molecule is simpler, HCN, but we have a better basis set, which then makes the number of qubits explode. So now we have, and by then also the number of variational parameters, which is now nearly 17,000. And the number of gates is near 6.8 million gates, and the circuit depth is similar. So one energy evaluation is just out of question, of course. On a quantum computer, we estimate then the corresponding way that a single quantum run in this hybrid run is 300 milliseconds, and the time to solution would be 15 hours in the same sense. Now, and this is absolutely impossible for any classical supercomputer. Even if you can do the 69 qubit now on a classical computer, the execution time will be absolutely hopeless. So the primary challenge for quantum chemistry is not really memory size or the number of qubits, but it's the circuit depth. The large number of terms needed to map the fermionic molecular Hamiltonian onto a qubit register, and parameters needed to expand the electronic wave function, and the quantum circuit evaluations and iterations to converge to an accurate energy. So chemical accuracy is extremely challenging for NISQ era quantum processes, and it's all about gate fidelity and coherence times. Quantum chemistry is going to be challenging for any near future quantum computer. As you can see then, in 70 to 100 qubits, you need millions and millions of CNOT gates. And so it's impossible for present and near future high-performance computer. And it's obviously impossible for any quantum hardware at the present time. What about quantum futures? Where are we going? So let's see, for the next 10 years, it seems that the roadmap suggests that there will be 1,000 qubits around 2025. But for those qubits to be useful, it's totally essential that the gate fidelity increases so that you can have a high quantum volume. It's totally possible that the quantum volume will not grow with the number of qubits unless you are very good at improving the coherence time. The quantum software will be no problem because it will always make a maximum use of the available quantum hardware. This is the development of computers anyway all the time, that chemistry has always saturated any classical computer that was available. That's like Clementi at IBM in the end of the 20th century. Anyway, use cases, practical use cases concern optimization. Ising type cost functions, Hamiltonians, that can be directly mapped onto qubit hardware. No extra transformations. So it's really Ising type problems, optimization problems. And there the quantum adiabatic optimization algorithm is particularly interesting for routing, scheduling, financial transactions, etc. And probably there will be quantum advantage demonstrated, but for that you probably need a few hundred qubits, good qubits on a good platform. And that will be the challenge, to do that without error correction. When it comes to use cases in fundamental research, the variation methods for electronic systems is the important thing. And but there you cannot expect to do important calculations on quantum hardware for a long time. So you really need high performance quantum simulations to develop algorithms that use the hardware in the best possible way and sort of are efficient on that quantum hardware. And to achieve quantum advantage, time will see. In quantum chemistry, it's not going to be very easy. A kind of quantum advantage follows, of course, automatically. If a quantum computer can deploy a larger qubit space than can be stored on a high-performance computer. But the low quantum volume on that quantum hardware makes it likely that it will just produce noise. So if you want many qubits, you have to have very high quantum volume. Otherwise, it's just noise. But anyway, hybrid quantum computing is going to be well developed and surely drive the field. It's unavoidable. So beyond the NISQ era, beyond 2030, well, that's unknown territory. One is aiming for 1,000,000 qubits, but that will need quantum error correction. And if you have that, you will then only get a few logical qubits back, let's say 10 to 100. And you need about 100 logic qubits in order to get a sort of quantum advantage, because you need a number of qubits simply to beat a classical system. And quantum advantage will, of course, depend on applications and progress of high-performance computers. So what's there in 2050? Who knows? So who will win the race? So I simply say there are no goalposts. It's an open-ended race. The coherence and gate fidelities will decide the ultimate NISQ barriers and issues of quantum advantage. Scaling plus quantum error correction will decide which platforms can reach serious quantum advantage supremacy. And that's really up in the air. To do serious quantum chemistry, you may need 1,000,000 logical qubits. And that's really difficult. So those of you who are around 2049 will know or may know. So anyway, that's the year of the singularity, when the high-performance computers are supposed to become intelligent. We'll see. So anyway, around that time, maybe the killer application will be relevant, elucidating reaction mechanism on quantum computers, where you actually can do some useful work on enzymes of importance for chemistry and for lesser medical development. This project has been supported by the European Commission through the quantum flagship project, OpenSuperQ, and also by the Knut and Alice Wallenberg Foundation through the VACT project, which is my home project at Chalmers. And thanks for listening.